Welcome to E-Pathshala's lecture series on computer science. The subject is about Introduction to Visualization, and in today's module we are going to discuss about temporal visualization. Some of the learning objectives of today's module are we try to introduce the concepts of what temporal data is. We'll also learn the different approaches of temporal data visualization. We'll learn the visualization of representing or presenting temporal data in the form of a graph, and we'll also look at certain examples in temporal data visualization. Introduction to temporal data. The temporal visualization or timelines are similar to one-dimensional linear visualization because timelines are widely used and vital enough for medical records, project management and historical presentations, and they are considered as a separate data type. Temporal data is characterized by items that have a start and finish time, and items may try to overlap with each other. The timeline visualization usually include all the events before something or after the event occurred or during some time period or a moment. Some of the examples of temporal visualization include the timelines, the Gantt charts, the stream graphs, arc diagrams and thread arcs, tree rings, concentric circle graphs, time series charts and graphs, and alluvial diagrams. Let us now have a look at the different approaches to visualizing the temporal data. Countless charts and visualization represent time in especially the same manner. Usually a horizontal line, that is the x-axis, is divided by the temporal units that progress from the left to right. The vertical y-axis has some kind of quantitative measure as such. The x-axis provides an anchoring point for the independent variable, while the y-axis is a must for dependent variable. The time has a strong independent streak as such. For example, the outside air temperature can depend considerably on the time of the day. It's measured, but the time of day doesn't depend on the weather condition. The x-axis is clearly not the end of the line for incorporating the time dimension in graphical representations of data. The temporal information can form rich tapestries of patterns that needs to be visualized in various ways, and it is to be fully understood and supposed to be appreciated. There are many possibilities for representing the times and techniques to make interesting temporal patterns perceptible. As always, creating the best design involves considerations of goals, audiences, context, the nature of the data, and the capabilities and constraints of the system that is being used. Often, it isn't possible or desirable to show all the data that has been captured in a given span of time. So, the key is to use transformations and representations of data, and that reveal the important but otherwise hidden patterns. As Megan Mondre, an IBM researcher who worked on temporal visualization, displays at the University of Maryland, notes the pieces of the data that get abstracted or removed should depend on the type of the questions that you are going to be asking. Different tools are designed to support different types of questions as such. So this is an example which shows the power of the line graph, which has been done very long before. So this is, here you can see the x-axis is timeline which starts from 1700 to 1780 years. So here we can see how the balance was against and the balance was in favor of England. In the late 1700s, William Playfair set the stage for how many of us automatically think about representing the temporal dimension, that is a line graph. Line graphs are ubiquitous because they are a simple, precise and powerful way to represent the temporal data. Although displaying time as a progression from left to right take along a horizontal line has become ingrained in many people's thinking, there are notable exceptions as such. So if we look at the flow of the time diagram, here we can see how the time diagram goes right from the left hand side to the right hand side corner within some time period. So here we can see the variations in the time period with respect to the data that has been captured. So in his iconic flow map of the Napoleon's catastrophic 1812 invasion of Russia, Charles Minard blends and bends temporal and spatial representation. The path and number of outward bound soldiers is represented by an initially thick tan ribbon. So there is an initially thick tan ribbon that represents the path as well as the number of outward bound soldiers, while the dwindling number of retreating survivors are represented by a narrowing black band. In this visualization, the time it took to march into Russia is not very clear. The only timestamps shown are for the return trip and processing from right to left. In a sense, time is bent to advance the impact of visual narrative. So if we can see, we can have a look of how the invasion has occurred starting from the left hand side to the right hand side as such. So this is another one example of a time series dataset which represents small multiples and a big store chain dataset as such. So in this, if animated visualizations are highly compressed movies that showing changes over time, and small multiples are sequences of freeze frame images in which we can discern the overall patterns and also focus on individual elements as such. The visualization show the growth patterns in the expansion of the Walmart store chain in US over time. So starting from one particular time, we can show the growth, we can see the growth of Walmart, how it has changed, and now at present how it has grown to this extent when compared to the initial starting point. So this is the small multiples of a big store chain. This is a near real-time data set which has been captured at October 30, 2012. The speed and the average speed of the wind is being clear. We can see how the wind speed changes with respect to each and every region, how it has changed, and the wind power also is being represented in the form of a legend. So at any given time, we are only able to take in a limited amount of information about the world around us. So this is at a specific time, say October 30, 2012, and at a specific time. So generally, that view is actually narrowly focused on our immediate surroundings. Some visualization can distill and reveal otherwise hidden patterns of the activity occurring in near real time. The uses of these displays can also range from a defined practical purpose to a more experimental and thought-provoking quality. Here's an example of the latter which shows the ever-changing wind pattern moving across the US in real time. The lighter the lines, the higher the wind speed. So this is an example of the near real time scenario which is being represented in the form of a map. There is a logical order and typical timing for many of our daily activities. So it is possible for us to visualize the relationship of events over time. Beyond the familiar routines, there are many other kinds of chronologies that can have an impact on our lives but can be hard to discern. Increasingly, we are able to collect and analyze many patterns of actions and events in data that would be otherwise imperceptible. Ben Schneiderman and Catherine Pleasant, with their colleagues at the Human-Computer Interaction Lab at the University of Maryland, have been grappling with the challenges of visualizing various kinds of temporal patterns contained within large aggregations of data as such. So this HCL's team approach to this kind of analysis was to build an application called Event Flow and then apply this to analyzing the data, including the collections of the electronic health record, that is the EHRs. In order to understand the way their application works, there are two key terms to know, that is, point events have a single timestamp. Examples, online shopping transaction, selecting an item or purchasing an item. In the case of hospital admittance, it is admit to some specific hospital. The interval events take place over periods of time, durations with starting and ending points. So this is an example of the interval time, that is the time an online shopper spends on a particular website which has a starting time and an end time. Similarly, the duration of a third quarter in a football game which has a starting time and the ending time, and we can visualize the events that occurred within this starting and the ending time. Investigating the patterns and relationship in both point events and interval events over time can quickly become a complex task. So this is some kind of visualizing the relationships of events over time. Here we can see the point events. The vaccination precedes the symptom by 1 week. which can be inferred using this figure. We can see we have an injection here, you have the symptom, which means the vaccination precedes, and each and every point represents 1 week, basically starting from June 1st to June 30th. So here we can understand that the vaccination precedes the symptom by 1 week. So we have 2 different symptoms and 3 or more symptoms try to develop within 1 week. That is an inference that we get from this timeline event. Similarly, the point event during an interval event, stroke occurs while taking drug A. So here we can see within an 8 weeks time period, you have the stroke, the drug A has been started, and drug A is the end time at which the drug has been ended, and in between we can see the stroke occurs, which tells that the stroke has occurred within the time the drug has been taken. Similarly, we have multiple interval events, that is when the drug A has been started and when the drug A has ended. Similarly, the time at which drug B has been started and drug B ends. So this task becomes even more demanding if the goal is to compare and investigate similar sequences of events in many hundreds or thousands of records, as is partially shown in the screenshot. Even in this case, with only 5 of the 215 records that are shown, it is difficult to make any kind of meaningful comparison in the time and sequence of events. However, making these kinds of comparisons can be useful in gaining insights about processes and procedures that happen in the hospital. So this is one data set. So this shows various data set, the starting of a particular drug that has been taken, the ending time of a particular drug with various multiple drugs that has been taken. So this is a time series data set that has been included in an EHR. By creating a graph from the data that is a layer or the table, we can also visualize the changes in the graph or the underlying data over time by simply enabling the time on our data set. There are numerous graph types such as bar, line, area and scatter plot graphs that can be used for visualizing the temporal data as such. The type of graph that we use depends on the data and how you want to visualize it over time. Common examples of graphs to animate data through time include some of these. Attributes are plotted on the y-axis and time on the x-axis or vice versa. Some examples include a line graph with stream flow on the y-axis and the time plotted on the x-axis, or a scatter plot graph as in the example the graph below with water, gas and oil production plotted as 3 series on the y-axis and the time plotted on the x-axis. So we have the lost soldier field production, we have the time series, the time starting from the left hand side to the right hand side from 1978 to 2006, and we have the water, gas and oil, which are represented as 3 individual lines here. The attributes are also plotted on the x and y axis, that is, this includes a bar graph with population or disease on the y axis and country on the x axis. This is the country is represented in the x axis and the population change, the population is represented in the form of a bar graph. So in the graphic below, the state name is plotted on the x axis and the population is represented on the y axis. Since there are repeating features for different times, this is represented on the form of a bar graph. When the layer of the table is used to create the graph above, it is time enabled and is visualized over time using the using the time slider. The graph will only show 1 bar per state for each sequential time slice. For example, in the graphic below, the population value for the year 2000 is displayed for each year. This is a population for the year 2000. So there will be a time slider by the side. If you change the time slider, the entire bar graph will change as per the value that is represented in the time slider. Why to visualize the data through time? There are many reasons that you might want to visualize the data through time, such as some of the following. Exploring the historic patterns in data such as population or land use changes, tracking the hurricane paths and other meteorological events, mapping the progression of a wildfire or a flood, examining the change in ozone through some kind of elevation levels, or visualizing the changes in the occurrence of a disease with respect to time. So any supported layer or table can be visualized over time by following the steps below. Enable the time on the data. Once added in the arc map, arc globe or arc scene, a layer can be time enabled by setting the time properties of your layer on the time tab of the layer properties dialog box. And then we can go in for the usage of the time slider, where the time slider allows us to step through the time enabled dataset in arc map, arc globe or arc scene. In the current air traffic control environment, the air traffic controllers use several visualization systems, namely the radar views, timelines, electronic strips, meteorological views, supervisions, etc. This kind of information is displayed intrinsically temporal, that is, aircraft positions that evolve over time, conflicts between aircraft at a given time, and the airspace congestions with respect to time. Each of these visualizations is rich and dynamic. It also displays numerous visual entities that move and evolve over time. Furthermore, this considerable volume of information must be understandable with the minimum cognitive workload. So as the traffic increases and safety criteria becomes more demanding, this air traffic control requires this new kind of visualization, the time and visualization. Burton was the first to define representation rules that produce a non-ambiguous representation, the semiology of graphics. This semiology is a complete system composed of signs and rules which permit the building of a planar maps or diagrams. This kind of system is a powerful tool to represent, memorize, understand and communicate the information. Semiology also describes and explains the perceptual phenomena and properties underlying the act of reading an abstract graphic. Burton also tried to introduce variables that are used to code the information visually, namely the position of the data point, the size of the data point, the orientation of the data point and the color of the data point. Burton did not provide special rules for time representation. These graphics address a major event to show temporal data with a static representation. These views are not a simple time series or timeline views. Burton's work was used to characterize the design choices. Design choices were compared with objective criteria as such. Finally, new visualizations were created to improve the image efficiency. One visual design that codes the temporal information, that is a radar comet that is being used by the air traffic controllers. The radar comet. It is very difficult to create a new design without any kind of support. Nevertheless, we identify several different methods when building visual entities. An empirical approach is to design based on trial and error methodology. A historical approach is to design based on the continuity of the previous work with a concern for adaptation for the given context. An ecological approach is to design based on the respect of both physical and perceptual human factors. And a technological approach is to design based on the technological opportunities. The design proposed to be investigated is a radar comet. It instances all the mentioned sources of design, and the first design source is an ecological design source. So this is a Haley's chart of the trade winds that was built up in the year 1686. So here we can see in one zooming factor wherein you can see some particular portion of the trade winds that are being shown here. The direction, a comet's visual properties were used for the first time in the early 17th century by Edmund Halley, who coded the trade wind direction on the map. He also coded the flow in the form of a stroke. So the flow of the wind is represented in the form of a stroke. The comet has accurate design properties. It displays the direction of the shape and the tendency. The comet is composed of a bigger part, its head, and a smaller part, its tail. Its head indicates the comet heading and the tendency indicates the direction of the wind. The curvature of the shape indicates whether it is turning right or left and the degree of veering. This design is an ecological design in so far that it stems from our basic understanding of motions, and an ecological design is usually easily understandable. So these kind of air traffic control visualization derives some benefit of this comet, and the design of the first radar comet is historical and technical in nature. So this is the figure that shows that the shape decreases in intensity over the time on a scope. This is a comet metaphor which is being shown on the right hand side. So it is not directly based on the Halley's design but on early radar equipment which relied on scope persistency. Older radar scopes retain the previous plot position with the fading of the screen phosphor. This kind of design has the same remarkable properties as a Halley-style comet in that it displays aircraft trajectories, curvature tendencies, and show if an aircraft is turning and the degree of veering is also being shown in this diagram. The ODS is a main French radar view for the air traffic controllers, and its main goal is to display the aircraft position and to help the air traffic controllers to space the aircraft beyond the security minimum. The radar track also represents the air traffic's position, speed, the name, altitude, and the speed of text. So this is a French radar screen which also shows that kind of visualization. So this is a ODS coded information wherein the aircraft position is encoded as a visual code in the form of a position. The aging of each position is represented as size. We can see here as the aging increases, the size also decreases. The aircraft tendency from left to right as a comet curvature, that is represented here. Similarly, the aircraft acceleration, that is a regular or irregular point spacing, shows the aircraft acceleration as such, and the aircraft entity is represented with respect to proximity and size basically. Proximity is the nearness of each and every object that is placed on the screen. So this is how the ODS coded information is transformed into a visual code. So for instance, the aircraft tendency data is not needed to draw the comet, but the comet nevertheless codes this kind of information. The emerging process stems from the embedded time in the radar plot positions, and the time can be easily derived into speed and acceleration. The comet design is an efficient visualization of data time. The fact that the underlying data is temporal helps the reader to interpret naturally emergent information such as the speed, the tendency, and the acceleration. Viewing these kind of geospatial and temporal data simultaneously is actually very difficult. It is therefore desirable to do so in order to identify the geo-temporal relationship that might show the movement trends or where a terrorist plot might culminate into some kind of attack. So enhancing these kind of geo-temporal data visualization involves the intelligence data that is being displayed with multiple views, that is overlaid with numerous data points, connections, and details. This data can then overwhelm the display surface of the single monitor. Maintaining the context within the large data set is actually challenging because it is mentally demanding to remember what was seen previously, where it was, and the potential relationship to the current information. A gigapixel intelligent analysis navigation tool was invented to implement the solution to these kind of problems. Use of node linking techniques similar to the type are often employed to represent social networks and a geospatial visualization that place the nodes over top a map in their appropriate position. The geo-temporal problem was addressed by mapping activity age to the opacity of the edges between the nodes. So this is an interaction with the help of this giant, that is a gigapixel intelligence analysis navigation tool, which was implemented to solve some of these problems. So this is interaction with a giant. For example, a phone call that occurred several days ago would be represented by a faintly transparent edge between two nodes, whereas an opaque edge indicated the current activity. A separate timeline view was also included, but the edge opacity allowed a basic understanding of the event ordering without requiring users to switch their focus to a different view. The remaining problems were addressed by using a high-resolution tiled display. It allowed us to show greater amounts of data at once while still presenting the multiple views. There was sufficient area for the data to avoid traditional information visualization navigation strategies such as panning and zooming, overview and detail, focus and context, and their associated problem with maintaining the context information. By designing to take advantage of the increased pixel count, the implementation of many features were not possible with a single monitor solution and was done. So this is a giant social network graph that has been shown here. Using this, we can better understand how to integrate the time and the geospatial data simultaneously in a single view. Experts in information visualization and HCA field evaluated different methods of conveying this type of data. The rapid prototyping techniques were paired with formal user evaluation to understand the effective ways to analyze or in finding the threatening events and the persons. These methods were then used to explore the benefits and challenges associated with using high resolution tiled displays for intelligent visualization. During system evaluation, it was found that combining the geospatial and timeline views offered a more efficient means to search than using isolated views. Users also located specific nodes faster with the timeline view because node names were shown as an index. Geospatial searching also improved with the location-based nodes because users relied on the familiarity with map geography. Lastly, the large tiled displays overcame many smaller display shortcomings. Yet still they require filtering and other methods to reduce the amount of data that are shown on a single window as such. So some of the examples of these kind of temporal data visualization are a stream graph, which is a technique that is used for displaying large-scale time series data based on the dataset and can be used to overlay multiple time series data. This kind of visual could be used to illustrate changes in sales volume over time for different products. Because of the thickness and color of each stream, it is more compelling way of showing the temporal data than a stacked bar chart. So this is an example of a stream graph where we can see how much each and every data set has been viewed by entire person. So this is the kind of data set. Facebook, here comes Google and Yahoo with respect to time. So this is a starting time, this is the end time that the stream graph has been, the data has been taken. This is another example of the data set which shows the project starting time with what are the tasks that are completed and when it was completed. Till the project ending time, we can see what are the various subtasks and when those subtasks were being completed or when it was implemented with respect to the time series data. So this is another rectangular view of the data set, a visualization of the temporal clustering of meteorological time oriented data from the Potsdam observation station. This is a meteorological data set that was taken with respect to various time starting from 1960 to 1997. This is another example of the temporal data. So here each shape shows how one film did at the box office as such. So starting from June till February for each and every year, we can show the height shows actually the weekly box office revenue of each and every movie, and the area of the shape and the color corresponds to the film's total domestic gross. So the gross income from that film is represented with respect to the color information, and what are the various films. The film information is also given here with respect to timeline. This is being seen. So in the summary, we can say that we have looked at the introduction to temporal data, the various approaches to visualizing the temporal data, and how to visualize the relationship of events with respect to time. The temporal data visualization for air traffic control has been taken as a case study and has been dealt with in a detailed manner. The geo-temporal data visualization has been studied, and some of the examples of temporal data visualization has also been looked at. Thank you.